Assalamualaikum and hi. So today I would like to present Hini laser system for assignment 1 SSCP4513 laser physics. So this is our team members from group 1. I'm Erina Hazika, Monica Sarah, Nur Shahira, Rabata Adarwiya and me Nur Elisha.
Before we go to the detail of helium-neon laser system, I will introduce you the introduction to helium-neon laser system. So this laser was first demonstrated in 1960 by Ali Javan, William Bennett and Donnelly Harriot at Bell Laboratories. So one of the earliest and most important gas lasers was developed in laser technology, and it is first laser capable of producing a continuous wave laser beam. It uses a mixture of helium and neon gases inside a low-pressure discharge tube. As we can see from Hini laser system, electrical discharge excites helium atoms which transfer energy to neon atoms to produce simulated emission, and the optical resonator with mirrors amplifies the light and produces the laser beam. The most common wavelength Hini laser system usually is 632.8 nanometer, and it produces red visible light. And one of the major advantages of the Hini laser is its excellent beam, stability, and high coherence length compared to many other laser types. However, the system generally produces the relatively low output power, which is typically in the range of few milliwatts and requires a larger setup compared to compact semiconductor laser. Overall, the Hini laser system represents a significant milestone in the development of modern laser technology and continue to play an essential role in optic laboratories.
So now I will explain the pumping mechanism in the Hini laser. In the Hini laser system, pumping occurs through electrical discharge inside the gas tube, which is shown inside the image attached. A high voltage is applied across the tube, which causing electrons to accelerate at high speed. These electrons collide with helium atoms and excite them into metastable energy state. The excited helium atoms then will transfer energy to neon atoms through collisions. So this process will excite the neon atoms and creates a population inversion. Once population inversion is achieved, stimulated emission occurs and the laser produces a red light at about 632.8 nanometers. So overall, the Hini laser uses electrical energy as the pumping source, and the laser action will depend mainly on electron collisions inside the gas mixture.
So let's look at the section 3.2, which is the active medium. So the helium neon laser is actually a combination gas of helium and also neon. The ratio is 10 to 1, and the gas is sealed inside a narrow 1 mm tube gas or glass tube. So actually the helium is inside the atoms, but the neon atom is actually the one that produces the light. So as in the diagram shown here, the electricity passes through the tube and inside the helium atom. So then the helium atom will collide with neon atom that actually will pumping them up to the higher energy level. So once the neon atom drop down to the lowest energy level, they will release a photon. This transition will create a visible red laser beam at exactly 632.8 nanometer. So this gas has a low gain coefficient or small signal gain and 1.5 GHz line rate, which due to thermal movement. So to keep the laser running continuously, the lowest energy level will clear out very quickly to maintain a stable population inversion. Thank you.
This slide explains the laser resonator in the Hini laser system. The Hini laser uses a Fabry-Perot linear resonator. It consists of two mirrors facing each other. One is the high reflector mirror, which also known as HR mirror, which reflects almost all the photons back into the cavity. The other is the output coupler mirror, which is known as OC mirror, which allowed a small amount of light to pass through as the laser output. The main function of the resonator is to provide optical feedback. It reflects photons repeatedly inside the cavity, which increases the photon density and enhances stimulated emission. This will produce a coherent laser beam. The resonator length will depend on the laser design. For standard system, the cavity length is usually between 15 to 50 centimeters, while for specialized system can be up to 100 centimeters or more. This resonator length is important because it determines the longitudinal modes and affects the frequency spacing of the laser. Overall, the resonator is essential because it amplifies light and helps to maintain laser operation.
Okay, now let's discuss about the section 3.4, the output coupler mirror. So, for standard helium neon laser, the mirror has a high reflectivity of 99%, which means only 1% of the light is transmitted out to become external laser beam. So, we need this high reflectivity to satisfy the threshold condition. So, what is the threshold condition? As shown in the slide. Yeah. So, because neon gas has a very low single pass gain, any bit loss inside the cavity will immediately stop working. Any bit loss inside the cavity will stop the laser from running continuously. So, a 99% reflectivity mirror keep our resonator loss low enough to balance again, so the laser can oscillate continuously. So this forces the photons to move forward and back an average 100 times in a tip. So this will trap the light and build a huge internal density, photon density inside a tube that will making the inside of tube is 100 times brighter than the output laser itself. So if we lower this reflectivity, the laser will immediately stop working. So therefore 99% reflectivity is vital to maintain a stable and continuous wave output. That's all. Thank you.
Now, I will explain the CW laser output generation of the Hini laser based on this diagram. So, first of all, let's assume a population inversion process on the left side. So, when the electrical discharge is applied on the discharge tube, the helium atom become excited into metastable energy level. And this excited helium atom then collide with neon atom and transfer their energy. So, as a result, more neon atom occupy the upper laser level compared to the lower level laser. This condition is called population inversion, where N2 is greater than N1, and population inversion is important because laser amplification can only occur when more atoms are in the upper energy level. Next, we move to stimulated emission and optical resonator. So, an incoming photon interact with an excited neon atom and stimulate it to emit another photon identically to the first photon, and then both photons have the same wavelength, same phase, same frequency, and they travel in the same directions. So inside the laser cavity, photon bounce back and forth between two mirrors. One mirror is reflecting, while the other mirror is partially reflecting and act as the output of the. So this repeated reflection increases the photon density inside the cavity. So the higher photon density increase stimulated emission and cause optical amplitude. Now let us look at the rate equation treatment. So the first equation represents the population inversion equation, while the second equation represents the photon density equation. So this equation describes how the population inversion and photon density change with the time inside the laser cavity. So at the steady state CW operation, both dn over dt and ds over dt become equal to 0. So that means the population
conversion and photon density become constant with the time. Finally, we move to the threshold condition and CW output graph. So, laser oscillation can only begin when optical gain become greater than or equal to the total optical losses inside the cavity. So, these conditions is written as gain greater than or equal to the loss. So, below threshold, laser oscillation cannot occur because photon losses are larger than gain. Once the threshold is reached, gain exceeds losses and laser oscillation started. So at the steady state condition, the photon generation rate becomes equal to the photon loss rate. Therefore, the Hini laser produces a stable continuous wave red laser beam at wavelength 3632.8 nanometers.
Lastly, the conclusion is the continuous wave laser system produces continuous laser output through constant pumping, and the pumping creates population inversion in the active medium. So, the active medium provides gain by stimulated emission, and the resonator provides optical feedback for light amplification. And lastly, the output coupler releases useful laser output, and the rate equation model explains continuous laser generation and stability. So, thank you.